Hello, everyone. Welcome to this concluding session in today's technical track for today morning. And the topic of my presentation here is the end of cold starts and autonomous concurrency within Sedai. So this is the objective of this session is I'll walk you through the history of cold starts, what causes cold starts, and what is the relationship between cold starts and concurrency. And what we're introducing as a part of this session is Sedai's offering to curtail cold starts using autonomous concurrency. And as we stylize autonomous as AITS, so it's that's what we mean by AITS here, which stands for autonomous. And I'll also walk you through how we eliminate cold starts and how the process actually works within Sedai. All right, to get started, right? So a brief primer on how lambdas work. To create a Lambda, you write your code either through serverless.com or SLS APIs or interfaces. There's numerous ways to do that, or you just directly write your code on the AWS console. Regardless, once you publish a package, what AWS does is takes your code, your runtime information, and all the required dependencies and packages it sort of like a container and puts it in somewhere and puts it in storage, like as in S3. So that's what happens when you publish a Lambda, right? So what happens when you actually start invoking the Lambda? Let's say there is an invocation in for your test skill Lambda, right? That's the name of your Lambda. The call is first intercepted by the Lambda service, right? That's the engine within AWS that intercepts all the service, the calls to the Lambdas, and make sure everything else is fine and set up before the Lambda is actually executed. So the first thing the service engine and the Lambda service does is go look up the function image from S3 or from storage, wherever it is, right? And takes a hold of that storage, the stored container. Then it looks at the Lambda, introspects it, and sees that it requires a language runtime, right? Maybe you wrote your Lambda in Python or Java or .NET, right? So it sets up the runtime environment and ingests the Lambda code into the runtime environment. And once all this is done, that's when the actual function is about to be executed, right? So all the steps that you saw here until the invocation of the function is what actually contributes to the cold start. It's getting the code library code from storage, setting up the runtime, preparing it, and initializing it, and all the things that you need to do before the actual function is executed. So this happens in the first invocation that this Lambda gets, or this instance of the Lambda gets, right? The second invocation, which let's say the first invocation completes and the second invocation starts, let's say a few seconds later. Now it doesn't have to go experience a cold start because the Lambda container or the runtime is already warmed up. It's ready to go. Lambda service just invokes that Lambda function and just returns back and does what it needs to do. So there's no cold start in subsequent invocations. But that's not true for all invocations from then on, right? What happens is AWS still has to allocate resources for you, even though you might not be using the service, right? For instance, you're between invocations and there's a longer lull, right, between invocations. So if the period of the gap between invocations is approximately around 7 minutes, AWS thinks, okay, that's good enough time to wait for an invocation. It shuts down the runtime and then removes it from memory, right? So a request that comes in subsequently after to that would again experience a cold start. So that's kind of the life cycle of the runtime and execution of a Lambda. Now, just to look at cold start by the numbers, right? From our analysis, we have found that up to 1.2% of invocations are actually cold starts in any given typical implementation with a decent enough invocation seasonality and invocation variation in the number of invocations. But that 1.2% of calls that's causing a cold start has been seen up to 13% of the total execution time, right? So you're spending 13% of your time just getting the Lambda to be ready to execute, right? So that 13% of execution time is time you could have spent serving customers requests or something else more productive, right? So that's the magnitude of the impact of cold start on your current infrastructure. Between 3 to 14 seconds is what you would see as typical cold start time, right? For a very a small Node.js Lambda, you might see somewhere around 3 seconds, up to 14 seconds that we are seeing for .NET based Lambdas, right? So the spread of time spent waiting for the container to be warmed up and ready to execute is in that range, right? So you're talking about 14 seconds that a customer might be waiting on checking out something from your card. So let's look at the impact of concurrency and cold start, right? So we understand what cold start is, but what happens when you have concurrent requests? And we are going to walk through a scenario to kind of elaborate on that. Let's say a customer is trying to get a quote for an insurance, right? Bought a new car and want to get a quote for how much should I pay for my insurance. So the customer makes a request for get quote, right? And this get quote is served by a Lambda, right? So, well, you spend a few seconds, a few cycles waiting for the Lambda to be ready for the invocation, right? So this is the init phase, this is the cold start, right? So that the red part is the time you spent in cold, waiting for the Lambda to warm up. And the actual green part, which is a smaller portion, is probably the time that you actually are executing the business function, right? So the customer still had to wait for that cold start before she gets the code from the insurance. The second code, right, from a different user or from the same user for that matter, now goes back to the same runtime environment, right? So now it's all warmed up, ready to go. So no cold start, everything happens much faster the second time around. Third request comes in, pretty much the same story, right? Things are quick and fast. But what happens when a fourth request comes in before the third has ended execution, right? So AWS service is that, well, there is no runtime available to satisfy this invocation, right? So it spins up another runtime, and now this runtime obviously again needs to go through that entire cold start process, and only after that is it actually executed, right? So this fourth customer who came in has experienced a cold start. What if a fifth request also comes in before the first or before the third or the fourth one has actually completed execution? Well, the fifth customer also experiences a cold start, right? So in this case, we saw 5 invocations and 3 of them actually experienced a cold start. Right? Now, admittedly, now as you go forward, as if there are no more concurrent requests in the future, then AWS just uses one of the existing runtimes. But then what I want to highlight here is during the initial phase, right, you experience a lot more cold starts while the runtimes are not up and available. Now, the solution to cold start from AWS is provision concurrency, right? And this helps solve the problem by a very significant margin, right? So what provision concurrency does in this case, Sector 2, is we are paying extra money to AWS saying that, hey, okay, let's just keep these 2 runtimes available and up. Don't let it die down, right? And so that whenever a customer comes in, they don't experience a cold start. And that was great, right? That's so the upfront time spent in actually that cold start is done before a request comes in, right? The provision concurrent instances are already ready, the runtime is ready and ready to go, right? So now the first request comes in, immediately served, no cold start. Second one comes in, great, no cold start. Third one comes in, again, goes to the same container, same runtime, no cold start. The fourth one goes to the second one. Now this is concurrent, right? Concurrent to the first one, which is why it went to the second one. Now the fifth one comes here, right? That has no available container, right? The first one is busy, the second runtime is again busy. So now AWS has to go back to the previous technique of spinning up a new runtime environment for the invocation, and the fifth customer experience cold start before the function is actually executed. So provision concurrency does help eliminate cold starts, but it doesn't do it 100%, right? Now you could set provision concurrency to 3 in this particular case, and you could have eliminated cold start for the third customer as well. But the problem here is provision concurrency it's a trade-off. It's not cheap, right? You have to pay extra money for just keeping those runtimes up and ready. So this is where we want to introduce the concept of autonomous concurrency. So what is autonomous concurrency? Well, there's a new feature that we are just making available in Sedai to autonomously manage your concurrency to reduce cold starts. This work with existing lambdas in production, right? There is no need for code change, no configuration change. As far as Sedai is concerned, it's a simple toggle button in the UI, right? You just enable it at a per lambda or throughout your account. It's your choice as a customer, but that enables autonomous concurrency for those lambdas, and it eliminates more than 90% of actual cold starts. So how does this work, right? Okay. And before that, this one actually requires just 3 days of data to start being effective, right? So you don't need to wait days and weeks for a model to actually pick up the seasonality pattern and other things to actually start being effective. This is pretty much effective in as short as 3 days of time after you turn on the toggle and made available. So how does it work, right? So what Sedai does is, behind the scene, similar to provision concurrence, Sedai makes activation calls that keeps the runtime warm, right? The runtime is ready before the first invocation comes in. So again, sort of similar to provision concurrency, the first request, the second request, the third request, they all go to the first runtime, no cold starts. The fourth one goes to the second runtime, no cold start, and the fifth one, again in this case, goes to the third runtime, and there is no cold start in this particular case. Now, you might wonder, how did we decide we needed three runtimes here, right? So that's part of the magic of autonomous concurrency, right? So we can keep more than sufficient, more than the warranted number of containers or runtimes warm and ready to go than the traffic, right? And this number keeps ahead of the traffic, right? So the way this works, actually, let me get to that as I walk through how we built it. So before I get there, let's compare this with other solutions to eliminate cold starts. One popular approach is to use warmup plugins, right? But warmup plugins is a decision that you have to make way ahead of your deployment process. A developer needs to be aware that they need to enable that Lambda for warmup plugin, right? And they have to make code changes during development to make it compatible with warmup plugin, right? And to do that in a safe manner. With autonomous concurrency in Sedai, this is a after the fact decision, right? You make a decision whether you need autonomous concurrency when you are in production. So there's no code change involved, no upfront planning. For warm-up plugins, you need to the code change is also necessary to make sure the safety of the execution is guaranteed, right? What if you make a warm-up call to something that's potentially, let's say, deleting some entries from a database, right? That could be probably disastrous if it's not done safely. But with autonomous concurrency, no code change is required, and it is inherently safe because of the way we built it. With warm-up plugins, again, you have to you have to know what is the expected concurrency, and you have to set those when you set up the warm-up process, right? Again, this is before your code goes into production. You don't know what your invocation pattern is before it goes live, right? So how can you make a decision on the concurrency setting, right? So it has to be a manual and an iterative process looking at production data and anticipated production data. With autonomous concurrency, all that is taken care of behind the scene, right? Sedai automatically adjusts for traffic, for seasonality, and it observes the actual live invocation of the Lambda, and based on that decides how much extra containers it needs made ready and ready to go. And the frequency of warm-ups, right? With warm-up plugins is again something you have to configure, and the 7-minute that we talked about, where AWS actually keeps a container warm, there's no documented evidence that it's just 7 minutes, right? It's purely up to AWS to say, but it's typically 7 minutes is what has been observed. But we have seen when it even goes down to a few minutes. So warm-up plugins do not adjust to those kind of changes, but with the autonomous concurrency, it's very dynamic and adjusts to every runtime shutdown events that we get from the actual running container, right? So it's completely tuned into the actual values and not like a hypothetical 7-minute value. Let's contrast this with provision concurrency, right? Provision concurrency, one of the challenges is you need to have a more stringent CI/CD process and a development process to make sure your Lambdas are versioned so that it can actually take advantage of provision concurrency. You cannot do provision concurrency on unversioned latest Lambdas. But autonomous concurrency works on both version and unversioned lambdas. So any lambda that you write would be able to take advantage of autonomous concurrency. Provision concurrency again requires upfront analysis to decide on the concurrency settings, versus autonomous concurrency does that all dynamically, looking at real-time traffic and seasonality patterns. You can do auto scaling with provision concurrency using the auto scaling feature within AWS, but this requires you to understand the concurrency limits and set thresholds and limits. Versus in autonomous concurrency, all that again is taken care of, right? There is no need to set up manual limits or thresholds. It's just one click of a button. The only decision you have to make is whether you want to enable it for the Lambda or not. With provision concurrency, there's also the potential of cost overruns if you do not plan on your concurrency and if you don't understand the utilization pattern of your Lambda. That's very critical, and which has been historically the reasons why a lot of customers were reluctant to use provision concurrency. Now with autonomous concurrency, there's no chance of cost overrun because it's continuously monitored, and again because of the way we have built it. Now behind the scene, autonomous concurrency does take advantage of provision concurrency when the alternative does arise, right? So you still get the best of both worlds with autonomous concurrency. So let's look at a typical invocation, right? Let's say 100 million invocations with typical seasonality variation, right? So it's not like a steady traffic, there's ups and downs. Let's say the average invocation is 500 millisecond and you're using 1 gigabytes of configured memory. So the monthly cost for something like that at 100 million invocations would be of the order of around $853, give or take, and you would see significant amount of cold starts given the 100 million invocation number. Now, if you set provision concurrency to 2, right, you definitely will eliminate a lot of cold starts, but you still have quite a bit, right? At 100 million invocations, you are definitely going to see a lot more containers spin up than just the 2 that is set by provision concurrency, right? And all of them will experience cold start, and the cost for that would be of the order of a couple $1,000. But with autonomous provisioning, we are actually adding a little bit more invocation, but the possibility of cold start has now gone down very significantly, but at pretty much at the same price point as without provisioning, right? So this is the advantage from a cost point of view when it comes to autonomous concurrency. So this is just a graphical view of representing the same information, right? The cost goes down, you still get the same benefits and better benefits than provision concurrency, but at a very significant lower cost point. So how did we do this, right? So what Sedai does, what we did for enabling autonomous concurrency is we built an extension layer that gets added to every Lambda, right? So we saw from the talk prior to this session from Sridhar how extensions help you do all these cool features within Lambda, right? So we took advantage of a lot of those features with extensions and build an extension that actually helps do this. The extension passively observes your Lambda, listens to lifecycle events, intercepts activation calls, and then within Sedai, within the backend system, we predict the seasonality for the invocation for the actual Lambda, and then based on that, we keep the number of the actual number of containers that or the runtimes that you need to keep up with the seasonality settings. We continuously validate this and issues activation calls to keep up with the concurrency values. And we tweak these parameters again continuously through reinforcement learning, right? You may deploy new Lambda, and then the invocation, the duration of the Lambda might change, right? So there's a bunch of things that could happen around, which could change the behavior of your Lambdas and the environment, and we keep up with that and tweak the parameters continuously. So what does it look like for you as a customer who may want to use autonomous concurrency? Well, we deploy a activation Lambda in your environment. That's the AV Lambda. And then we have, we store most of the cache a lot of the concurrency information in DynamoDB closer to you so that it runs in the same account and it's much less latency in terms of getting that information and acting on when a cold start is about to happen or when a container shutdowns, right? So this is what we set up initially to onboard you for autonomous concurrency. The customer Lambda itself is now decorated with Sedai's Lambda extension, and that's it, right? And all these things happen magically once you click that button on Sedai's UI to enable autonomous concurrency. So very briefly, the extension actually handles the activation calls. It collects the usage stats and listens for shutdown events. The activation Lambda request actually gets the data from Sedai core for seasonality and predicted concurrency numbers, and that's the one actually that issues the activation calls and keeps track of the concurrency settings, listens for shutdown events, and so on. So in conclusion, autonomous concurrency is a no-touch, no-code, and a fully autonomous solution built into Sedai to manage your concurrency setting. It eliminates pretty much most of the cold start with zero risk of cost overruns, right? So this, we believe, would be the final solution to end all cold starts. This feature is now available in general in Sedai, so all customers will be able to take advantage of this feature. And if you haven't tried this out yet, I request you to go to sedai.io and try it out yourself. All right, so that's pretty much all I had for this session. I will look out for questions for a few minutes. AB Jacob, who is our Director of Engineering, would also join us to field some of these questions. Thank you, AB. So the question here is, can autonomous concurrency work along with other optimizations? Yes, so the other optimizations we saw earlier in the day with memory, those are completely independent of autonomous optimization when it comes to concurrency. So yes, they all work together seamlessly with each other. So if you remind me about the number of extensions that's allowed, I think
10, I guess. Yeah.
10 extensions, right? So yeah. So yeah, you want to take this one, maybe?
Yeah. So the way we have built it, we don't think it will interfere in any way with the other extension that's already there, because we have done all the safety checks to ensure that all the warmup calls are intercepted within our extension, and rest everything passes through just normal.
Right, and AWS itself supports multiple extensions, right? So it's a feature that's a part of the platform to have multiple extensions live and not interfere with each other. So, and since we are focused very much on just the concurrency part, if there is another extension to focus on, let's say tracing or logging, or something else, right? They would all work nicely independent of each other. Right. Any more questions? I guess not. Okay. Thank you, everyone, for attending. Thank you, AB.
Thanks, Nikhil.
And next up, we have a 30-minute lunch break, and followed by a session on what is autonomous cloud. And I'm sure that's going to be interesting. So see you all in another 26 minutes. That's at 1 p.m. Pacific. Thank you, everyone.